This is section 4.2, Polynomial Functions and Models. These are the topics we'll be covering. Again, we have this very ugly definition of a polynomial function. Please don't get lost in the notation. Please understand the a sub n's, or the ak's, are simply your coefficients. These numbers up here are your exponents, and we simply be able to identify when something is a polynomial. Now, we've already seen several examples of polynomials. Constant functions are polynomials. They're simply all these terms up here don't exist. We simply have a constant term, degree 0. A linear function is a polynomial of degree 1 with just these last two terms. And a quadratic function is just a polynomial of degree 2 with these last three terms. As we talked about before, polynomials have certain features. One of those features was called a turning point. And a turning point, or what I already described, as peaks and valleys. The turning point, more specifically by definition, is when the graph goes from increasing to decreasing, or vice versa. In other words, the graph is going up, then it hits a peak, and then it comes down. That's decreasing. When we talk about increasing, we're talking about going up left to right. When we're talking about decreasing, we're talking about going down left to right. We're looking at the y values. Let's look at an example. In this example here on the left, we have one peak and one valley. One peak and one valley gives us simply two turning points. In this example on the right, we actually have two peaks and one valley, so we have three turning points. Let's go back and review some of the prior functions we've already studied. A constant polynomial function. This is just y equals, in this case, y equals 3, and in this case, y equals negative 2. Notice on each constant function there are no x-intercepts, except in the case where y equals 0, then every point is an x-intercept. And constant functions also have no turning points. For linear functions, notice linear functions have a single x-intercept, but linear functions also do not have any turning points. We looked at quadratic polynomials before. A quadratic polynomial can have 1, 2, or 3 x-intercepts. Here's an example. It can have 0, 1, or 2 x-intercepts. Here's an example of 0 x-intercepts. Here's an example of 1 x-intercept where it goes up and just touches the x-axis and comes back down. And here's an example of 2 x-intercepts where it passes through and then comes back and passes through again. All quadratic polynomials have a single turning point. We can look at cubic polynomials. These are simply degree 3 polynomials. And a degree 3 polynomial has 1, 2, or 3 x-intercepts. Here's an example of 1. Here's an example of 2 where it bounces, then comes back down and goes through. And here's an example of 3 x-intercepts. And a cubic polynomial either has 0 or 2 turning points. A quartic polynomial, that simply means degree 4, has up to 4 x-intercepts. Here's an example of 4 x-intercepts. Here's an example of 2 x-intercepts. Here's an example of 3 x-intercepts. We can actually take this graph here and shift it up where it would be 1 x-intercept, or shift it up way beyond this where there's no x-intercepts. And it also has, at most, 3 turning points. A quintic polynomial of degree 5 has up to 5 x-intercepts. Here's an example of one with 5. Here's 3. Here's 2. And it has up to 4 turning points. So based on our examples, we can develop some basic rules. For a polynomial of degree n, the graph has at most n x-intercepts. We saw degree 5 had at most 5 x-intercepts. Degree 4 had at most 4 x-intercepts. Similarly, it has at most n minus 1 turning points. Degree 5 had 4 turning points. Degree 4 had at most 3 turning points. So whatever the degree is, if it's 10, there's at most 10 x-intercepts. If it's 10, there's at most 9 turning points. Let's talk about the end behaviors of even functions. When we're talking about even functions, we're talking about degree 2 or more. And what we want to look at is for the end behaviors, we will look at the leading coefficient, that a sub n, that number in front of the largest degree term. For even functions, the end behaviors are always the same. In other words, the ends always go up or they always go down. Let's look at degree 4. This is an even function. Both of these are going up, both of these are going up, both of these are going down. Similarly with degree 2, both up, both down, both up. So with even functions, they're either both up or both down, and the way we can determine whether they're both up or both down is to look at the leading coefficient, the a sub n. If the leading coefficient's positive, they're both up. If it's negative, they're both down. Odd functions behave differently. Again, we have to look at the leading coefficient. Odd functions behave in the opposite way. One side up, one side down. Let's look at degree 3. Notice the left is down, the right is up. The left is down, the right is up. The left is up, the right is down. They behave oppositely. Degree 5. One side down, one side up. One side down, one side up. One side up, one side down. They behave oppositely. So how do we know? For odd functions, if an is positive, the left side goes down to negative infinity, and the right side goes up. So if we looked at this graph, we knew the leading coefficient here was positive because the left side down and the right side's up. We knew the leading coefficient here was positive because the left side's down and the right side's up. If the leading coefficient's negative on an odd function, the left side goes up and the right side goes down. So if we went back to our cubic polynomials, here the leading coefficient's positive because the left side down and the right side is up. Here the leading coefficient is negative because the left side is up and the right side is down. So let's look at these graphs and see what we can apply. Here is a function. How many turning points do we have? Well, we have 2 valleys and 1 peak, so there's 3 turning points. There are 1, 2, 3 x-intercepts. We know the degree of the function is even because the left side goes up and the right side goes up. And because they both behave the same, we know they're even. And since they both go up, we know they're positive. So determine the minimal degree of the function. I know it's an even polynomial with 3 turning points and 3 x-intercepts, so the degree has to be at least 4. Let's look at an example of looking at a function determining what happens based on the equation. F of x equals 2x to the 4th minus 3x cubed minus 2x squared. The degree is simply degree 4. What we do is we look at the exponent. The highest exponent is the degree of the function. In this case, this is degree 4. The leading coefficient, I keep referring to that. All we do is look at the leading term. That's the term with the highest exponent, which is x to the 4th. The leading coefficient is the number out front, so this is 2. State the end behavior. This is degree 4, so they both either go up or they both go down. In this case, they're both going to go up because the leading coefficient is positive. So f of x goes to infinity. In other words, it goes up as x goes to both infinity and negative infinity. In other words, as I go far to the right, the function goes up. As I go far to the left, the function goes up. Last thing we want to look at is piecewise defined polynomial functions. We've already done some of this. Remember, we sometimes have to define a function on multiple pieces. Remember the numbers, the intervals to the right define the domains, and the pieces on the left define the actual function the way we have it defined. So when I look at f of negative 4, we simply look at negative 4 as our x value, and we look at each of our pieces. Is negative 4 less than negative 2? Yes, it is. That means I'm going to plug into the top piece. Negative 4 times negative 4 is 16. Our next one is f of 3. 3 is not less than negative 2, but 3 is between negative 2 and 3 because this says less than or equal to 3. So I'm going to plug this into the middle piece. So 3 cubed minus 1 is 27 minus 1, which is 26. Finally, f of 5, it's not less than negative 2. It's not between 2 and 3. It is greater than 3. So I'm going to plug this into my bottom piece. So 3 minus 5 is negative 2.